In this tutorial, we're going to cover an introduction to Grasshopper. You can either start by opening up the reference file, which I have opened, both open up Rhino and then open up your Grasshopper window, or you can start a new file as I will just hide display on all of these components so we can go through and rebuild each one. In both the introduction to the Rhino interface and Python, we went over some basic principles of creating points and creating lines from those points, creating polylines, as well as several other geometry types. We're going to start with a similar introduction to Grasshopper by first constructing a single point. You can navigate through the Grasshopper components through these tabs. At the top, the first tab is parameters, then you have mathematical operations, sets to work with lists, then a panel for vector operations, curve, surface, mesh, and then you have intersections. So this is going to include Boolean operations as well as just standard intersections between UREFs and lines. Then transformation, so this is going to be your move, scale, and rotate operations, as well as several other things. And then we have display. So those are the only tabs I'm going to get into now. The rest of these are plugins that I have, so we can just leave it there at the moment. So we're going to start by double-clicking in the Grasshopper canvas, and we are going to type construct point. So we can see that it generated a preview inside of Rhino, and when we click on the component inside of Grasshopper, that preview goes from red to green. This lets us know that we've selected that component, and that is the geometry we're referencing inside of Rhino. When we hover over each of these letters on the component, we can see that on the left are inputs, and it tells us this is a type number or float. So 0.1 indicates that it's a float input parameter, and it tells us that it is the x coordinate of that point. Then we have the y coordinate and the z coordinate. If we hover over the middle, it tells us that it's a construct point component, which constructs a point from x, y, and z coordinates, very similar to both Python and the Rhino interface. And then if we hover over the point at the end, we can see that there is a point output of an x, y, and z value, and then the geometry preview inside of Rhino. So if we want to adjust the location of this point, we can double click in the canvas and type any number, or we can type a number, so let's say 0, and then we can do a less than sign, and then the maximum number in our range, so let's say 10. And this now gives us a slider from 0 all the way to 10 as only integer. So we can plug this into X, and already as we slide this, we can see that the Y and Z are still 0, but we are updating the X value based on our slider position. So right now X is 0, and then 1, 2, 3, and so on. We can hit Alt and left click and drag to copy these down, and then plug each one in, and this allows us to control the X, Y, and Z separately. If we didn't want to just move the original point, but we actually wanted to make a copy of this point, we can use a move component by double clicking and typing move, and plug the point into the move component. And if we hover over the T, we can see that it takes in a vector translation, and by default that vector translation is 0, 0, 10. So that is going to be a vertical vector pointing straight up with a length of 10. We can do something very similar that we just did with constructing a point, but instead construct a vector by typing vector x, y, z, and then enter. And then we can plug this vector into the translation input parameter, and then we can just copy these x, y, and z sliders and plug them into x, y, and z for our vector. So we now have one point at 4, 2, 8, And then we have another point at 8, 4, 16. So I'm just hovering over that G, and we can see the output of that moved point. If we adjust this vector, we can see that it updates the coordinates of this moved point. Since we have these 2 points in space, we know that that can make a line. So if we just double click on the canvas and type line, then we can see that the bottom option for line is actually a parameter which would reference a geometry already drawn, but we haven't drawn out that line and we actually want to reference the points inside of Grasshopper. So we're going to just use the second option with the 2 endpoints and a line between them. We can see that this takes an input A, which is a starting point, and an input B, which is an ending point, and it outputs a line segment. So if we plug in the output parameter of this point and the moved point, we can see that it has drawn that line between those 2 points inside of Rhino. Grasshopper allows us to keep the relationships between each of these components even when we move the initial input sliders. So as we move this, we can see that it is in real time adjusting both the point and the line that these sliders are connected. If we wanted to not just make one additional point, but similar to the exercises in Python, if we wanted to make several points moving along the x-axis, in Python, what we would want to do is use a for I in range or for x in range, but in Grasshopper, we're actually just going to input something called a series. So double click and type series and enter. And then we can hover over these input parameters and we see that it needs a starting number of the series, a step, and then a total count. So if we want to make 10 new points, then count 10 works. The start at 0 will also work, and our step can be 1. Now, since we only want to adjust the location in the x, if we plug in the output from the series into our x input, we can see that it has made a series of points moved along the x-axis. So that is a point at 0, 0, 0, 1, 0, 0, and so on. If we plug this series into each of those components, we can see it makes a diagonal line moving from 0, 0, 0 to 1, 1, 1, and so on. Now that we have a list of points, we know that a list of points can be used to generate a polyline. So if we type polyline and then plug in our output of those points into the V for vertices of that polyline, we can see it generates a polyline. We can also do this with a curve, so degree 2 and higher curves, but at the moment we just have a straight line. So we're going to want to make some edits here so that we're not just generating a straight line. One way that we can do this is in Grasshopper, we can use things called a graph map. And we can actually take this output of the series, so these 10 numerical values, and plug them into this graph mapper, and then we can plug the output of the graph mapper into the X. And then if we just right click on the graph mapper and go to graph types and click Bezier, what this component is going to do is remap the values based on an input range to an output range related as it relates to the curve on the graph. So right now we have a range input from 0 to 1 and an output from 0 to 1. So we want to change this to match our series, so 0 to 10. So I just double clicked on that graph and then changed the x1 value to 10 and the y1 value to 10 as well. Hit the check marks and then the OK. We can now see that our y and z values are still going to be 0 through 9, but our x values are 0 through 8.8 and are mapped according to the curve shown on this graph. If we use these handles to adjust the Bezier curve on this graph, we can manipulate our curve position. Right now, though, it's still just points in space and we haven't drawn a curve through it. So if we double click and type curve, all the way at the top, we can see NURBS curve. This is going to take, similar to a polyline, input vertices. So we can plug those points into the input vertices. And then it's going to take an argument for the degree of curve, which degree 3 is fine for now. So we can now in real time adjust this curve based on our point positions. If we copy this graph down by hitting Alt left click and dragging, we can then do this for each axis and edit the curve in 3D. Now that we have this curve output, we're going to go through a process of creating geometry from this curve. So this is just one example. There are many ways to create any type of geometry inside of Grasshopper. This process is going to involve dividing this curve, extracting perpendicular frames along that curve, and then lofting between profile curves relative to those perpendicular frames, making that lofted geometry solid, and then making some transformation adjustments like we did with these graph mappers so that we have some control over the outcome geometry. So the first thing to do is to make a divide curve component. And we can see that this takes an input curve parameter and a count. So if we plug in our curve, it will divide our curve at the moment into 10 segments. And it gives us an output set of points, tangents, and curve parameters. So in this case, it goes from 0 to 7, and we can see each of those parameters printed out below. If we double click and type perp frame, you can see that perp frame takes as an input a curve and a parameter input. So we have a curve output from our earlier process that we can plug into the curve input, and then we have our parameter values from those divisions. What perp frame does is it draws a frame or a plane perpendicular to the curve at a given curve parameter. So in this case, our division points. We can see how those perp frames rotate with the curve. This allows us to cleanly sweep geometry and have control over each individual profile section along this curve. There are many other ways to do this with different methods for division, but we're going to just stick with this for now. So we don't just need the perpendicular frames, but we actually need a profile section relative to those perpendicular frames. So in this case, we're going to create a rectangle by double clicking. So this is going to give us a rectangle at the origin. So we can see that it's the XY plane by default, with an X size from -1 to 1 and a Y size from -2 to 2. If we wanted to, we could right click on that Y, go to set domain, change this to -1 to 1, and that will give us a square. Now we just have that square at the origin, and it's also visualizing that origin plane in the XY plane. So if we want to get those onto these perp frames, what we need is to orient them. So if we double click and type orient and enter, we see that orient takes a base geometry, an initial plane, and a final plane. So in this case, our initial plane is going to be the XY plane that the rectangle is generated on. Our reference geometry is going to be the rectangle, and our final plane is going to be our perpendicular frames. We can see that each of those frames are generated flowing along this curve. Now, once we have that, we can already double click and type loft, and this would allow us to loft between each of those profiles, and we can go back to the start and adjust our curve and see that updating in real time. But this doesn't give us any control over the actual sections along the curve. We've just made one reference rectangle and that's it. So if we want to make adjustments, we can do something similar to what we did with the points and making the input curve. This time though, we're going to add rotations to these oriented planes. So if we double click and type rotate, and the rotate component is going to take a geometry input, an angle, and a plane. By default, the angle is in radians. If you right click and select degrees, it will change that to degrees. And our plane in this case, we want to be the perp frames, so that way it rotates on that. Now, one way that I like to manipulate these rotations along the curve, there are many ways to do this, but I like to use the parameters and make a remap component, so type remap, and this is going to take a number value and remap it from a source domain to a target domain. So if we plug in our parameters into V and then double click and type bounds, this is going to give us the minimum and maximum from those parameters, so 0 to 7. So that would be our source domain, min max of these values that went into the V. And then our target domain right now is 0 to 1. If we right click on this and set domain, we can make this 0 to 180. And if we plug this now into A, we can see that that is rotating from 0 at the first point to 180 at the last. And if we plug these rotated rectangles into the loft, we get rotation along the curve. But this is a consistent rotation all the way along the curve. If instead we want some control over this, we would want to use a graph mapper. So I'm going to just copy one from where we had it to the left and use this output remap number value to plug into the graph mapper. And we can click into the graph mapper and change our input, so the X value to 0 to 180, and then we can change our output to 0 to 180 as well, and plug that into the angle. So now if we keep both of these at the bottom, it's just going to be no rotations, just following the perpendicular frames. But as we lift this off, we'll start to see rotations based on the parameter values on the curve. Once we have this, before we get into the Boolean operations, we want to make sure that this output is a closed brep, otherwise it's not going to work with our Boolean operations. So right now it is an open brep. If we double click and type cat holes, then plug our output in, and it will create a closed brep. Now, a quick way of starting to operate on this with solids is to make a bounding box. So double click and type bounding box, hit enter, and we're going to just draw a bounding box around this curved geometry. And then we are going to allow for variable scaling of this bounding box so that we get a kind of clipping on our original lofted geometry. So to make a variable scaling, we can double click and type NU scale, so that's scale non-uniform. And this takes an input geometry, a plane, and an X, Y, and Z scale factor. Right now, we want our plane not to be the XY world plane. Instead, we want it to be the center point of the bounding box. So if we type volume, we can actually get an output from the volume, which is the volume of a geometry and the centroid of that geometry. So I'm going to just take this output box, plug it into geometry. We can see we now have a centroid of that box, and we can use that centroid as our base plane for the scaling. Now we just want to double click and make a slider from 0 to 1.000. This decimal will give us precision in the slider, so if we hit enter, it's no longer an integer slider. Instead, we can cycle through 3 decimal place precision. And then I'm going to copy this 3 times and plug each one into its own axis. Now we can see we've scaled that box based on the centroid, but we aren't actually intersecting or operating between the lofted volume and this box volume. So what we want to do is double click and type solid intersection, and this solid intersection component is going to work similar to a Boolean intersection inside of Rhino. So it takes a first set and a second set of B-reps. So that will be our lofted geometry in our box. And then if we just then select over these components, click the scroll wheel and click the blindfold, it will disable the preview. And we can see we get our intersection between these 2 volumes. As we adjust the scale, we can decide how much of the original lofted geometry is trimmed. In order to get that geometry into Rhino, as you can see, we can't click on it right now. One way that we can do this is to click on the solid intersection, click the scroll wheel, and then click on the egg, which will bake this object. This will send it from the Grasshopper environment into Rhino. And we can now see that we can click that object inside of Rhino. It says one closed poly surface added to selection. We can use the gumball to move it around. And because we know that we've created this using a parametric process inside of Grasshopper, not only is it easier to iterate through and update the geometry, but we also have control over the geometry itself. So we know that this is going to be a singly curved geometry, which means that we can click on this and type unroll surface, enter, and we can unroll each of the panels of this object, which means we could cut these out of paper and make a paper model that would exactly represent this object. This is going to be really helpful for quick fabrication as needed in the program to supplement robotic fabrication. One last thing to note is that we don't need to just do this process with a bounding box volume, but we can actually copy this solid intersection and use the original solid intersection as the A input, and we can actually make a different type of volume. So let's say a cone, hit enter, and now this cone is going to take a base. So right now we're going to just leave it at XY. That way we can perform rotations and then move it. Then it takes a radius and a length. So I'm going to make a slider from 0 to 30, copy it, and we're going to use those for the radius and the length. So now that we have that, it's still oriented at the origin and it's only pointed up. So we may want to be able to control the rotations. So I'm going to double click and type rotate, but we don't want rotate in plane. This time we actually want rotate 3D. And rotate 3D takes an input geometry, an input angle, which again we can right click and select degrees, a center of rotation, and then an axis of rotation. So in this case, it's going to be the origin, which is where our cone is instantiated. But the axis we actually want to be able to control so that we can control the axis of the rotation. So this is going to take an input vector. If we double click and type vector X, Y, Z, hit enter, and then we can just copy these X, Y, and Z sliders and plug each one into the X, Y, and Z vector. Now, the last thing we need is the angle input. So I'm going to double click, type 0 is less than 180, and then plug that into the angle. Now we can see that we have a cone that rotates about a specific vector as its axis, and adjust the angle at which it rotates and the axis around which it rotates. So if we disable the preview on our base cone and then plug this output of this rotated cone into our solid intersection, you can see now we just have a very small sliver, but if we adjust the angle of rotation or the axis of rotation, we can see how the cone differently intersects with this reference object. Now, this cone though is still rotating only at the origin, and we may be able to get more useful geometry if we move that after its rotation to the centroid of our bounding box. So we want to move this, but we don't want to move this based on the origin point. Instead, we want to move it based on the centroid of this geometry. So we know in a cone, we have the tip of the cone, and then we have the length of the cone. So if we divide the length by 2 and then subtract it from the tip of the cone, we should be able to get the midpoint of the cone. This is not the volume centroid, but it is the midpoint of the length of the cone. So we're going to take this tip output and we are going to make a unit z, which is a vector in only the z-axis, and then we can plug our length slider into this component and it gives us a z vector with length 22. Now we don't want it to be positive, so if we just right click on our F, there's an option for expression which allows us to change this slider input. So in this case, if we wanted it to be negative, we could say negative x, and this would give us negative 22 instead of 22, which it does. Then if we right click again, we want this to be half of that value, so divided by 2. This should give us negative 11, which it does. Now we can plug that into the move component and we get a moved point from the tip of that cone. If we didn't want to use the move, with vectors and points, we can actually mathematically add and subtract them. So instead of moving, we could just say addition, and we could add the tip point, and effectively we're subtracting or adding a negative vector, and we get a new generated point. So we can see the original is 0, 0, 22, the output is 0, 0, 11. Now we want to create a vector from this point to the bounding box centroid, so we can type subtract, and we are going to subtract our desired location, so this bounding box centroid, from our current one. We can see right now that the cone is a bit too big, so there are no actual intersections there. So if we just shrink it down a bit, maybe increase the size of our bounding volume, now we can see the cone is intersecting with our lofted geometry. We can bake this again, and because a cone is also a singly curved geometry, we know that we can unroll this one as well. That's all for this tutorial. Try to be creative with this, construct multiple curves, maybe draw a curve in Rhino, set it inside of Grasshopper, see if you can get some shapes to interlock, see if you can build up multiple, or maybe even use this method to generate an input into the aggregation script. So we could bake this out and then we could set this in our aggregation script as the brep to explode. This may make a mess depending on your geometry, but it's worth giving it a shot and trying to get these methods to start to come together.